Good morning, class.
I'll get back.
So, good morning, class. You're welcome to another round of Chemistry 101 lecture. Recall that 2 days ago, we started electrochemistry. And electrochemistry comprises of different aspects, which include electrochemical source of energy and electrolytic cells. 2 days ago, we considered electrolytic cell. Mouse, problem. Mo ti gbàgbé pé screenshot ni. So, good morning once again, and sorry for the short break. Recall that we started with electrolytic cells 2 days ago. Today, before we move to electrochemical cells, which is another very important type of cells that should be considered when we talk about electrochemistry. Recall that I promised to finish up some of the examples that we started 2 days ago. And before we go on to electrochemical cells, which is the plan for today, I will want us to quickly finish up some of the problems that we couldn't finish 2 days ago when we started this topic. We were trying to provide solution to this particular question. The volume of hydrogen liberated at STP at the cathode during an electrolytic process in 30 minutes is 1,120 cubic centimeter. What quantity of current was consumed? The question, from the way it was put, you will realize that the process is supposed to be guided by first law of Faraday, which states that the mass deposited or dissolved at the electrode should be directly proportional to the quantity of electricity that is passing through the electrolyte. Now, looking at this problem, we have been told that the volume of hydrogen liberated at STP during an electrolytic process in 30 minutes is 1,120 cubic centimeters. So the reaction was performed under standard conditions, standard temperature and pressure. And we have been given the time, the duration of the process, and the volume of hydrogen that was liberated. And this cathode means that, of course, that is where we expect the hydrogen to be liberated, because remember, it is the negative electrode. So hydrogen ion is going to migrate towards this electrode, the cathode, and it's going to absorb electron on that electrode, and it will become deposited according to this reaction equation. So hydrogen atom, all right, but hydrogen gas does not exist as an atom. So that means this equation would have to be properly written to produce hydrogen gas. And that is what we have here. So which means that 2 Faraday will be required to liberate 2 Faraday, because we have 2 electrons here. It means 2 Faradays will be required to liberate 1 mole of hydrogen gas at the cathode. 1 mole of hydrogen gas at the cathode. So knowing that, we can then write this simply, all right, equals A over ZF Q, all right? So this is the equation arising from the first law of Faraday, okay? So now that we have been told the volume produced, okay, we have been told the volume produced, we can always determine the current, that is the quantity of current that was required. So we also recall that Q equals IT. The time has been given, so we need to know the quantity of electricity. which we can obtain from here. We need to know the quantity of electricity, and which we can obtain from this expression. Okay, so M, which can stand for the volume obtained, okay, over A, okay, equals Q M over A equals Q over ZF. All right. So we are not going to be talking about mass now, because what we were given is volume. We were not given the mass. So we cannot relate mass and volume. So invariably, we can relate volume and the molar volume of hydrogen, which is 1120 over 22,400, which gives Q over ZF. The Z is 2 according to this equation. 2 and F we know is Faraday's constant, 96,500. Okay, so we can obtain our Q from there. All right, and that is exactly what we have done. Okay, but this is just simple proportion. This is another alternative that can be used. You can just use a simple proportion, that since you know that 2 Faraday will be required to produce 1 mole of hydrogen gas, okay, and these 2 Faraday, okay, that is said to be required to produce 1 mole of hydrogen gas. The volume of hydrogen, 1 mole, the volume of 1 mole of hydrogen, recall, is 22,400 cm3. Okay, and that is what we did here. The volume is 22,400 cm3. So if 2 Faraday will be required to produce this volume, how many Faraday will be required to produce this volume? That is what we did here. And if you don't want to use this simple proportion, you can also fall back on this. All right, and that will give you Q to be equals 193,000, okay, 193,000 times 1120 over 22, 193,000 times 1120 over 22,400, which is exactly what we have here, and then we get our quantity of electricity. But Q is not the problem that we were asked to solve for. We were asked to solve for the quantity. And so you call this relationship Q is IT. I equals Q over T. So the current consumed is going to be 9650 coulomb, which we obtained here, over time. The time is going to be in seconds, 30 minutes times 60. And that is what will give us the current. So the current will be 5.36 A. All right. And you know that in that process, you need dilute acid as your electrolyte. So as you produce hydrogen on the negative electrode, the cathode, you are going to produce oxygen on the positive electrode, the anode. So the equation that is associated to liberation of oxygen or production of oxygen on the anode is here. So this is just a simple form of writing the equation. This is not necessarily the actual equation that represents the process, but at least it is enough to give us the information that we need. And that information is that we will need 4 Faraday. From this, we will need 4 Faraday to produce 1 mole of oxygen. If we go back to the question says if 11 amperes were consumed, so we are done with this. The answer for that, the quantity of current that was consumed is 5.36 ampere. So the second part of the question says if 11 amperes were consumed in the liberation of 9400 cubic centimeter oxygen at 750 millimeter of mercury and 40 degrees Celsius, what time elapsed in the course of releasing this amount of oxygen? This time around, we have been given the current, the amount of current that was used, all right, and the volume produced. But a tweak to the question is that that process was not conducted under standard condition, because the pressure at that moment was said to be 750 millimeter of mercury, and the temperature was not at room temperature. Okay, it was 40 degree Celsius. So we need to find the equivalent volume that will be equivalent where the process meant to occur under standard condition. If the process was to occur under standard condition, what would be the volume that will be produced? It's not going to be 9400 as it is, because this condition is not the standard condition. A standard condition will require a pressure of 1 atmosphere, which is equivalent to 760 millimeter of mercury. So you are going to use the combined gas law to determine the volume that 9400 will be equivalent to if the experiment were to be performed under standard condition, which is P2 V2 over T2. Okay, so P1 is 750 millimeter of mercury. Okay, your V1 is 9400 cubic centimeter, and your T1 is 40 degrees Celsius. So what will be your P2? Your P2 is going to be the normal pressure, which is the standard pressure, 760 millimeter of mercury. 760 millimeter of mercury. Your V2 is what you are now looking for. All right. Your T2 is going to be 273 Kelvin. All right. So substituting these values, we will obtain the equivalent volume of the volume that is equivalent to 9400 cubic centimeter if the experiment were to be performed under standard condition, and that is 8091 cubic centimeter. Now, going back to the question, what time elapsed in the course of releasing this amount of oxygen? So we go back to the relationship. 4 Faraday will be required to produce 1 mole of oxygen, and the volume of 1 mole of oxygen is 22,400. So 8,091 was produced. Okay, under standard condition, 1 mole will be equivalent to 1 mole of oxygen will be equivalent to 22,400. Okay, and that will give us Q over 4 Faraday, 96,500 Coulomb. So we can get our Q from here. All right. If you don't know the relationship I used there, it is just simply that relationship we obtain from the first law of Faraday, which is KQ, where K equals A over ZF. All right. But this time around, we are relating molar volume to volume. Okay, not mass to relative atomic mass. Assuming these were given in masses, we would have used mass to relative atomic mass, but volume was provided, and so we have to relate volume given to the molar volume of the gas. And that is why we have 8,091 over 22,400. So from here, we can obtain our Q. And if we do that, this is what we are going to get as our Q. 139,425 coulomb. And then from there, we can obtain the time that it will require to finish this electrolytic process from Q equals IT. The Q is known, so I is given as 11 ampere, so T is going to be Q over I. So the value of Q can be imputed, and the value of I given, which is 11 ampere, can also be imputed. Now, let me quickly give you the first attendance code. The first attendance code is 9V-DW2. 9V-DW2. V stands for violet, or Victoria, or Victor. 9V-DWT, DW2. 9, figure 9, letter V, letter D, letter W, and figure 2. I hope you got that clearly. All right. So that's the first code. All right. So from here, we will obtain the time. And if we impute our value of Q, which is 139,425 over 11 ampere, so 139,425 coulomb, we are going to get this time in seconds, okay, and this the equivalent in minutes and also in hours. So that is that about that. So I just try to show the different methods that can be used to obtain the same answer. All right. So that is what I have here. Then another problem that we can also look at is this that I have before us. During the electrolysis of a salt of metal M, a current of 0.50 ampere flows for 32 minutes, 10 seconds, and deposits 0.325 gram of metal. What is the charge on the metal ion? And the relative atomic mass is given as 65. So this is a walkover. There's nothing really serious about this question. What this question is asking you to find is Z. You know, the magnitude of Z. So it's been said to be a metal. So metal is expected to be positively charged. Isn't that correct? So we know already that it's going to be positively charged. We are only looking for the magnitude of the charge. So we can relate the equation from the first law of Faraday to this. A over ZF multiplied by Q. A over ZF multiplied by Q. So what we are looking for is Z. Z is what we are looking for here. So just substitute, all right? So what you have is Z equal A over M, A over M, F, Q. So that is if you make Z the subject of the formula. So the relative atomic mass is given as 65. So Z, what we have there is 65, okay, over M. Oh. So the relationship again is Z equals A over M F Q. So if we put the corresponding values, we have 65 over 0.325 is given the mass deposited, 325, okay, multiply by Faraday, 96500, multiply by Q. So how do we get our Q? So our Q will be obtained from this information. We have been given the current, which is 0.50, multiplied by the time, 32 minutes, 10 seconds. So that is 32 times 60 to convert it to seconds, okay, and then plus 10. So we have the time in seconds, and we get our Q. So if we do that, we will get 965 coulomb as our Q. All right. So and then if we put the corresponding values, we are going to get 2 as our Z, which is what we are being asked to determine. So another question that we can also quickly look at before we start the normal plan for today is this question that I have before us. The concentration of cadmium chloride solution was 0.75 moles per dm cube. 5 amperes were passed through 500 cm cube of the solution in an electrolytic cell containing platinum electrodes. What is the concentration of the solution after 4 hours? What is the concentration of the solution? What is the concentration of the solution after 4 hours of electrolytic reaction? I would also like to let me quickly give you the second code, attendance code. VY 6VY, VY 6VY, VY 6VY, V for Victoria, Y for Yam, figure 6, V for Victoria, Y for Yam, VY 6VY. So we have been given the concentration of the electrolyte, and the electrolyte is cadmium chloride solution at the beginning of the reaction, electrolytic process. All right, this is the concentration. So 5 amperes were passed through. So the current that was passed through is 5, the value is 5 amperes, 500 cm cube. So it means the volume of the solution is 500 cm cube. All right, in an electrolytic cell containing platinum electrodes. So the electrodes were platinum material. So what is the concentration of the solution after 4 hours of electrolytic reaction? So the first thing we need to do is to determine how many moles of the cadmium ion or chloride ion were present at the beginning. All right, and that you can obtain from this relationship. Concentration equals number of mole over volume. Number of moles over volume. So the number of mole is concentration times volume. So concentration is given as 0.75 mole times volume in dm cube, which is 0.5, okay, dm cube. So at the end of the day, we are going to obtain the initial number of mole, which should be about 0.375 mole or thereabout. 0.0375 or thereabout. I can quickly, okay, 0.375 mole. 0.375 mole. So what is the concentration of the solution after 4 hours of electrolytic reaction? So the concentration means that we need to know how many moles of these reactant molecules, okay, were left after 4 hours of the electrolytic reaction. First, we can determine the quantity of electricity that was required. Q equals IT. Okay, I was giving us 5 ampere times the time, 4 times 60 in seconds. So we are going to get the quantity of electricity which was required. So that is 72,000 coulomb. And then since we know that 2 Faraday will be required to deposit 1 mole, okay, of cadmium, 2 Faraday will be required to deposit 1 mole of. So what mass of cadmium will be deposited in the presence of this amount of electricity? 72,000 coulomb of electricity, okay? And that will be obtained using this relationship, A over ZFQ, okay? A over ZFQ. And we really do not need to be asking for what is their relative atomic mass of cadmium, since we know that M over A will give us the number of mole, and that is exactly what we need, the number of mole that will be left after 4 hours of the reaction. So if we have that, that means that number of mole can be obtained using the relationship Q over ZF. So the Q is 72,000 coulomb, then Z is 2, and Faraday is 96,500. So if you put that, you are going to get 0.373 mole. That is the number of mole of cadmium that have been deposited during the electrolytic 4-hour electrolytic process. During the 4-hour electrolytic process. Remember that we have determined the initial number of mole that originally was there before the reaction started. And now we have been able to determine how much cadmium would be deposited. So what will be left in the solution is going to be what we started with and the amount that would have been deposited. So what will be left in the solution is 0.02 mole. So the difference between what we started with, the number of moles that we started with, and the number of mole of cadmium that will be deposited. So we find the difference and we know the number of mole that will be left in the solution. So the new concentration will now be the number of mole, the new concentration of the solution will now be the number of mole left in the solution over the volume, the total volume, because the volume will remain the same. It's not going to decrease. So the volume is 0.5 dm cube. So with 0.5 dm cube, we are going to get the new concentration of the solution to be 0.004 mole per dm cube. So now that is the end of some of the examples I have for you for electrolytic cells. And if you think there are still areas where you need more explanation, you are free to consult with your tutors at the tutorial, your various tutorial classes. You are free to consult with them. And if you are if you can make it to get me, I'm not asking for every one of you to look for me, but a few of you that can make it to get me, I may also be able, definitely, I will find time to be able to clarify any area that you may be having difficulty with under electrolytic cell, okay, or electrolysis, electrolytic process, electrolysis. All right. So now I think it's time to give the third code. It's time to give the third code. Let us give the third code. The third code is D, Z. Yes, thank you, Anim Bo IO112. Yes, it shows you are following. Yes, the number of mole is 0.375. Thank you. So again, the third code, DZT7F. DZT7F. D for dog. For Tayo. Figure 7 and F attendance code. Now we can move on to what I actually planned for today, and that is moving on to electrochemical cells. What is the difference between electrolytic cells and electrochemical cells? For electrolytic cell, you require an external EMF to propel a chemical reaction or to trigger a chemical reaction. If you remember, you have to connect to a source of EMF that will cause chemical reaction to start in the electrolyte. So you have two electrodes and you have electrolyte. The two electrodes will be connected to an external electrical energy source, okay, which is your battery. All right. So you need a battery to cause an electrolytic reaction to occur. All right. So that is a conversion of electrical energy to chemical energy. All right. So electrolytic process or electrolysis convert electrical energy to chemical energy. However, for electrochemical cells, you are using chemical energy to produce electricity. For electrochemical cell, you are using chemical energy to produce electricity. And the simplest type of electrochemical cell that we can talk about is called galvanic cells. Galvanic cells. And these galvanic cells are generally referred to as voltaic cell in honor of Alessandro Volta, who invented the voltaic pile that was regarded as the first battery. So each of these voltaic pile represents a cell, all right? And which means that ordinarily, when we have all these small tiger battery, we always refer to them, I just call it battery now. We always refer to them as battery. They are actually not batteries because batteries are a combination of multiple cells. A combination of multiple cells. That is what a battery is. So those things that you see around these torchlight batteries, tiger batteries, and so many examples of them, they are actually cells. The proper name for them is cells. Okay, so you have to have multiple cells connected together, okay, before you can have a battery. All right. So Alessandro Volta invented the voltaic pile that was regarded as the first battery. Even though a battery consists of multiple cells, the word battery and simple galvanic cells are commonly used interchangeably. So the simple cell is not rechargeable, cannot be rechargeable. Okay, all these simple cells are not rechargeable, but mostly the battery, okay, the battery, soon we shall be talking about cells and battery, and we'll be able to see the difference between cells. Okay, we'll see properly the difference between cells and battery, and that will be the next topic after electrochemical cells. So to illustrate what galvanic cells are, all right? And it's a very simple cell, very simple to construct. In fact, every one of you should be able to construct a simple galvanic cell. And how do you prepare, or how do you construct a simple galvanic cell? You need a zinc rod. An example of a simple galvanic cell is the Daniel cell. The Daniel with double L, Daniel cell, is an example of a simple galvanic cell. Look at the names I've used here. I've used voltaic. Voltaic generally refers to galvanic cell, okay, is a general name for galvanic cells. And a particular example, and there are many of such, cells. When we say galvanic cells, there are many examples of such, but a particular example is the Daniel cell, which we shall use to illustrate this concept. Okay, so this is a Daniel cell. So you have before you a Daniel cell. What does it make up? It is made of two electrodes. You have two electrodes. One electrode is made of zinc, is a zinc rod electrode, and that is the anode. The anode, okay, dipped in a zinc sulfate solution. You have a zinc sulfate solution as the electrolyte for that. And the other side of the electrode, okay, you have copper rod as the electrode, okay, copper rod as the electrode, and a copper sulfate solution as the electrolyte. To complete the circuit, you need to have a salt bridge, and the salt bridge can be made with potassium nitrate. A filter paper soaked in potassium nitrate can be used as a salt bridge. So when you connect using a connecting wire, conducting wire, okay, when you connect the two electrodes together, you are going to produce electricity. There is a potential difference between these two electrodes, and that will give you some amount of electricity. And this electricity is enough. The amount of electricity you can produce in this type of cell is enough to power a bulb. It's enough to power a bulb. So you can see you have converted chemical energy, chemical reactions occurring in the two electrodes. You have converted it to electrical energy. We are using chemical reaction to produce electricity. And that is the difference between electrochemical cell and electrolytic cell. So we are using chemical reaction to produce electricity in electrochemical cell. Whereas for electrolytic cell, you are using electrical energy to cause a chemical reaction to occur. All right. So now, with this setup, what is happening in this setup? How is it able to produce electricity? Okay, you need to be familiar with your electrochemical series. You need, please, I will implore you to please go back to your physical chemistry textbook to look at your electrochemical series. All right, zinc is a very reactive metal compared to copper. All right, zinc is a more reactive metal compared to copper. All right, for that reason, the zinc rod, okay, dissolve into solution. The zinc, and for that reason, zinc, okay, is higher in electrochemical series. Okay, if you are talking about the arrangement, the value of the reduction potential to reduce zinc 2 to zinc plus 2 electron to zinc is going to be more negative compared to that of the value to reduce copper 2 to copper. So as we go on, you shall understand better what this actually means. All right. So how does this cell able to produce current? All right. That is what you need to understand. So the zinc rod dissolve, okay, to produce zinc ion into the solution. As it is dissolving, this is the reaction that is taking place. Zinc zinc dissolves to produce zinc 2 plus, and in the process releasing electrons. So the electrons being released, okay, flow out of the electrode to the external circuit. And recall that anytime you have flow of electron, you know, what you have immediately is flow of positive charge, which is current. So as the electron flows in this direction, current flows in the opposite direction. The current will flow in the opposite direction. Okay, so that is the source of the electrons that is causing the flow of current. The dissolution of zinc to produce zinc 2 plus, leaving out 2 electrons. And once the electrons are generated, of course, current must flow. It's a must. All right, it's a must. And what is happening as a result of this in this electrode? We call this half cell. This is a half of the cell, and this is another half of the cell. So what you have here, the reaction occurring here is a half cell reaction, and the reaction occurring on the other side of the cell is another half cell reaction. So when you put the two together, that is when you now have a cell. Half cell plus half cell equals to a cell. So the whole of this is a cell. However, it is constructed by putting together two half cells. Okay, I hope I'm communicating. We are not talking about connection in series, because I can see some of you are saying some things here. All right, the Daniel cell, you don't have a cell. If you have this as an individual, you have zinc electrode here and copper electrode here, you do not have a cell. It is until you join them together that you have a cell. What you will have is a half cell, and a half cell cannot produce electricity. So the question of connecting it in series does not arise. I hope that is clear. So you have a half cell connected to another half cell. Half plus half is 1, and until then you do not have a cell. But if you connect half cell to another half cell, that is when you have a cell. Okay, so I hope I'm clear now. Let me quickly round up about what is happening on this zinc electrode half cell. Okay, as you produce this zinc 2 plus, so you have, remember that what you have here is zinc 2 sulfate solution. So the zinc 2 sulfate solution already contains zinc 2 plus and sulfate 2 ion, sulfate ion and zinc ion in it. So you already have zinc 2 ion and sulfate ion in it. So you are producing more of that from the dissolution of the zinc rod. So you have excess of zinc 2 plus in this half cell. You have excess of zinc 2 plus in this half cell. All right. On the other half cell, okay, the electron that comes to the copper rod get deposited, get absorbed on the electrode, and is taken up by the copper 2 ion in the solution. So you have copper 2 ion here in the solution, because remember, the electrolyte is copper sulfate solution. You have copper 2 ion. This copper 2 ion picks up the electron and get deposited on this electrode according to this reaction. Copper 2 plus 2 electron to give copper. Okay, so it gets deposited according to this electrode. So how do we know which? So from these two equations, you will see that on the anode, what is happening there is oxidation. On the cathode, which is the other one here, which is our copper electrode, what is happening is reduction. From this equation, you can see that what is happening is reduction. So on the anode, you have oxidation. On the cathode, you have reduction. Okay, we have just 3 minutes left. Okay, reduction on the cathode. So what is happening on this other aspect? The other things that are happening apart from copper 2 ions, you know, moving to the electrode and getting deposited. As the resulting, the implication of that is that there will be less and less copper. The copper 2 ions in the solution will be decreasing. The copper 2 ions in the solution will be decreasing. So there will be depletion of copper 2 ion in this half cell. All right, and you are going to have excess sulfate ion. You are going to have excess SO4 2 minus. Remember, what you have there is copper sulfate solution. So the copper 2 ion will be deposited, and so leaving behind sulfate ion. So you are going to have excess sulfate ion in the solution. Whereas here, you are going to be having excess zinc 2 plus as a result of the dissolution of the zinc rod. Okay, excess zinc 2 plus here, excess sulfate ion here. How do you mop up this excess ion? And that is the role of the salt bridge. The role of the salt bridge is, one of the roles is to mop up excess ions that are in each of the half cells. So potassium that is here, okay, we mop up this excess sulfate ion that is in the copper electrode here, and the nitrate ion that is in the salt bridge would react with the excess zinc 2 plus in order to balance the number of ions in this half cell. So the nitrate ion here will react with zinc 2 plus to mop it up. So, and that will maintain a balance in this half cell. Whereas on this other half cell, the potassium ion. So here, nitrate ion we do the job. Here, potassium ion will do the job of mopping up the excess ions. The excess ions here is SO4 2 minus, while on this other side, the excess ion is zinc 2 plus. So our time is up. We are going to continue from there on Monday. And if you have any problem regarding what we have done so far, like I said, you can see any of your tutors from your various tutorial classes, and you can as well see me. I'm always available. You can as well see me, but I'll prefer that you see your tutors. That way, okay, it will be the efforts will be spread. Okay, the effort will be spread because you have different tutorial classes, different departments for different tutorial classes, and you have different tutors. You all can meet your tutors for further explanation. Thank you very much. I'll not be able to take questions any longer. Whatever question you have, you can try to put them together and see your tutors in your different tutorial classes. Thank you very much. Sorry, while waiting for the other class, while waiting for the lecturer for the other class, I think I can attend to a few questions. If you have any question, you can please raise it here so that we can quickly attend to them. Okay, Michael Covenant. That's a good question. He asked, he said, is the chemical reaction always initiated from the anode? Yes, a very good question. The chemical reaction is always initiated from the anode. And that is one of the things you need to do. You need to be able to identify which electrode is going to be your anode. And to be able to do that, you need to familiarize yourself with the electrochemical series. You need to familiarize yourself with the electrochemical series. How did I know that it is the zinc? Okay, because the zinc is more reducing Okay, it can easily undergo, oxidation by releasing electron. It releases electron better than copper. So it is the one that will release the electrons, and then that is where the electrochemical process begins. So you need to be able to, and because it is the one that will release the electron, it is the one that will be the anode. Anyone that will release, any electrode that will release the electron will be the anode. Anyone that will take up the electron released by the anode will be the cathode. So for you to be able to know this, you must familiarize yourself with your electrochemical series. I hope that clears it. Flow of positive charge, Adebisi Islamiyah. Okay, flow of positive charge is current. Current is positively charged. It is the opposite of electron. Anytime electron flows, current in one direction, current will flow in the opposite direction. We said that in our previous class. Anytime electron flows in one direction, current will flow in opposite direction. That is a rule. That is a rule. Okay, current must flow in opposite direction, and that current is positive charge. Is positively charged. Is a positive charge. Okay, they have the same magnitude as the charge on electron. You remember the charge on electron is minus 1.602 times 10 raised per minus 19 coulomb. That of current is plus 1.602 times 10 raised per minus 19 coulomb. So they have the same magnitude. The only difference is the sign of the charge. For current, it is positive. For electron, it is negative. So thank you. This will be the end of the class for today. And we will meet again next week, Monday at 8 a.m. Do have a beautiful weekend. Thank you.
Okay. Okay.
Sorry. Ejo.
Good morning, class. Sorry for the delay. This is 103. Behavior matter. The last time we were to look at Archimedes principle. So today we'll be going to just that point. Before now, we've come across that principle. And of course, before the Archimedes principle, we've talked about the Pascal principle as a consequence of gauge pressure. So Archimedes principle. So I was trying to relate to you that that principle actually forms the basis for which you can have a super tanker, that's ocean-going vessel, depending on the amount of water that can be displaced. So that can be displayed. So the super tanker or very large ocean vessel can actually go. But if you have shallow waters or shallow river, such ship will not be able to go. So which means there are people in the area of oceanography that actually will have mapped areas, routes, depending on your ship, where you can actually pass. So it's on the basis of that knowledge of the tonnage of such a vessel vis-a-vis the water volume that is available in a particular place. That's what will inform the area the ship can go. So, and of course, like I said, we know Archimedes principle. Then the same thing also is also possible when we have the plane, cargo planes that can actually carry big consignments. There are some cargo planes that can carry armor personnel carrier that can actually carry tanks, armor tanks. You can imagine the tonnage. So it will carry it and lift it up actually in the air. So it's on the same principle of understanding fluids. Okay. So Archimedes principle, as we all know, said when an object is partially or wholly immersed in a fluid, don't let us say water, the upthrust, or what you call the buoyant force, it's a force. The upthrust is actually, that is the push on such a body, should be equal to the weight, okay, of fluid that has been displaced. The fluid that has been displaced must be equal to, the weight of fluid that has been displaced must be equal to the buoyant force, or what we call the upthrust. And of course, that force is upward, and then it also has a magnitude equal to the weight. Sorry, M is subscript F, not MFG. M subscript F, then G of the fluid that has been displaced by the body. So you can write the buoyant force as M subscript F, then G, or what we call the upthrust. Where MF is the mass of the fluid that is displaced by the body. Floating. Then there's also something